Today, we're exploring the frontier of material science and robotics, a field where machines are becoming less like rigid metal contraptions and more like living organisms. We're talking about soft actuators, devices designed to move and change shape in ways that mimic biological tissue. They are at the forefront of innovation in medicine, manufacturing, and aerospace, because they can adapt to complex, unstructured environments in a way that traditional rigid robots simply cannot.
At the heart of this revolution is a remarkable class of materials, silicone-based elastomers. These materials have garnered enormous attention because they offer a superb combination of properties. They possess exceptional mechanical resilience, meaning they can stretch and bend repeatedly without breaking. They are highly biocompatible, allowing them to safely interact with biological systems. And they are adaptable, maintaining their performance across a wide range of operational environments. This collaborative review, drawing from the laboratories of Dr. Kunal Mondal and Dr. Rigoberto Advincula at Oak Ridge National Laboratory and Dr. Gagandeep Kaur at Howard University, dives deep into the latest advances in these materials. It highlights state-of-the-art fabrication techniques and emerging applications that are enabling next-generation soft robotics and even implantable medical devices. Let's begin by understanding what makes silicones so special. Unlike most polymers that are built on a backbone of carbon-carbon bonds, silicones are based on a chain of alternating silicon and oxygen atoms. This is the polysiloxane chain. The fundamental structure is a repeating SiO unit. This silicon-oxygen backbone is the source of many of silicone's unique properties. We can see two general forms: a linear chain, known as a siloxane, and a more complex, cross-linked three-dimensional network, known as a silicone resin. This underlying chemistry is the key to everything that follows. Soft actuators, in general, represent the next generation of materials engineered to mimic the adaptive and dynamic traits of biological tissues. Compared to rigid actuators, they can undergo large, reversible changes in shape, imitating the natural movement of muscles. This ability to change shape in multiple directions when exposed to a stimulus is incredibly useful in applications that require high compliance and flexibility, especially when interacting with humans or fragile objects. As a result, they're finding a growing number of applications in soft robotics, wearable systems, biomedical devices, and artificial muscles. The design of these actuators is heavily influenced by the responsive mechanical properties found in nature. A prime example is the simple expansion and contraction of our own muscles, which generate precise motion and controlled force without being damaged. Soft actuators follow these same principles, enabling massive strains, often over 500%, to provide incredible flexibility and mobility. This dynamism makes them ideal for applications where adaptability, performance, and safety are paramount, such as in prosthetics, exoskeletons, and medical implants. Among all the materials explored for these applications, silicone-based materials have emerged as unparalleled. They offer an ideal compromise, possessing excellent flexibility and high elasticity, combined with the requisite durability to withstand dynamic and repetitive movements. With high tensile strength and long operational durability, silicone actuators can endure continuous deformation without failure, even in harsh environments. Beyond these mechanical properties, silicones possess excellent biocompatibility. This is a feature of utmost importance for biomedical applications where direct contact with living tissue occurs. This characteristic safety allows silicone actuators to be integrated directly into medical devices, such as implants. This is critical in applications like sensors or drug delivery systems, where tissue irritation and toxicity are major concerns. A second major advantage of silicones is their ability to retain their mechanical properties under a wide variety of environmental conditions. They have excellent thermal stability, remaining flexible at both very low and very high temperatures. They are also chemically stable and resistant to UV light, oxidation, and humidity. This robustness expands their use into areas where reliability and durability are vital, such as continuous operation in space, underwater, or in extreme industrial processes. This unique combination of high elasticity, biocompatibility, and chemical stability makes silicones the most promising materials for next-generation soft robotics and biomedical devices. If we look at the history of this field, we can see a clear evolution. The journey began in the 1950s with simple pneumatic actuators.
Material innovations from the 50s to the 90s were focused on basic rubbers and silicone elastomers. But starting in the 1990s, we see the development of silicone-based flexible microactuators, followed by electroactive polymers and shape memory alloys in the 2000s. More recently, in the 2010s and 2020s, the focus has shifted to bio-inspired designs, self-healing materials, and machine learning-enabled actuators. This progress in actuator technology has been mirrored by advances in materials, moving from basic silicones to high-purity composites, nanocomposites, hydrogels, and self-healing materials. Consequently, the applications have expanded from early orthotics and experimental manipulators to today's medical tools, soft grippers, biohybrid adaptive systems, and even space robotics.
Now, let's take a closer look at the specific properties that make advanced silicone materials so powerful for these applications. We can think of them as a collection of interconnected strengths: high elasticity, biocompatibility, mechanical strength, thermal stability, and electrical insulation. First, high elasticity. Advanced silicones are defined by their capacity for large elastic deformations without permanent damage or failure. Most can achieve strain capacities well over 500%. This incredible stretchiness comes from their unique molecular architecture. As we mentioned, the silicone-oxygen backbone is more flexible than the carbon-carbon chains found in most organic polymers. The SiO bond is longer and allows for greater rotational freedom, which translates to more movement along the polymer chain. To exhibit this rubber-like elasticity, these long polymer chains are cross-linked into a three-dimensional network. In its resting state, each chain is coiled. When a tensile force is applied, the individual chains uncoil and straighten out. The crosslinks prevent the chains from pulling completely apart. Once the force is removed, entropy takes over. The chains naturally revert to their more disordered, coiled state, and the material snaps back to its original shape. The density of these crosslinks can be tuned to control the material stiffness. This inherent high elasticity enables efficient energy transduction in soft actuators, allowing for complex, muscle-like movements. This is fundamental for developing flexible and efficient systems for repetitive tasks, such as in manufacturing or medicine. In wearable exosuits and soft robotics, this ability to undergo significant deformation and then repeatedly return to its original form is essential for continuous movement and dynamic environments. Next, high strength. Current advances have led to silicone materials with high tensile strengths, typically greater than 10 megapascals, while still retaining their superior elasticity. This strength also stems from the intrinsic stability of the SiO backbone. The crosslink 3D network is highly resistant and effectively distributes stress across the material. When tensile stress is applied, the crosslinks prevent the catastrophic separation of individual chains. A higher crosslink density leads to greater resistance to deformation and cracking. This combination of strength and elasticity is critical. For applications in robotics or prosthetics, the actuator must be able to withstand loads, manipulate objects, and apply precise forces, all while remaining flexible. This durability enables continuous functionality even under constant load-bearing situations, which is essential for devices like robotic grippers or soft exosuits that need both robust strength and inherent flexibility from a single material. Building on this, we have biocompatibility. This is a key characteristic that enables the broad use of silicones across the health and medical industries. Their ability to integrate into biological systems without causing damage arises from their chemical inertness. The stable SiO-Si backbone doesn't react with tissues or biological fluids, which prevents the leaching of harmful substances and the degradation of the material over time. This drastically reduces the risk of inflammatory responses or allergic reactions. Furthermore, the surface of silicone is naturally hydrophobic with low surface tension, which helps prevent bacterial colonization and the adhesion of proteins. When needed, the surface can also be modified using techniques like plasma treatment or chemical grafting to precisely control its wettability and further reduce unwanted biological adhesion. Medical-grade silicones are specifically manufactured to be non-cytotoxic and non-immunogenic, meaning they don't trigger an immune response like inflammation or rejection. This is paramount for long-term implantable devices, where constant neutral contact with the body is required. This property is what makes silicones a foundational material for medical devices like catheters, implants, and wound dressings, and it is particularly critical for soft actuators intended for implantable uses, like neuroprosthetics or next-generation drug delivery systems. Another notable feature is thermal stability. High-performance silicones maintain their mechanical properties over an extensive temperature range, typically from as low as -50 degrees Celsius to over 200 degrees Celsius, with only slight degradation. This stability is rooted in the robust SiO backbone.
The SiO bond has a very high bond energy, around 450 kilojoules per mole, which is significantly higher than the CC bond's energy of about 350 kilojoules per mole. It takes a considerable amount of thermal energy to break this backbone, making it highly resistant to thermal degradation.
Additionally, the flexibility of the SiO-Si chain is vital. It allows the polymer to retain its elasticity even at very low temperatures, as shown by its very low glass transition temperature, which is typically below -100 degrees Celsius. At these temperatures, many other polymers become brittle and shatter. At high temperatures, this same elasticity allows the material to expand and contract with heat without suffering excessive internal stress or cracking. Silicones also possess extreme resistance to oxidation, UV radiation, and ozone degradation. This inherent stability makes them ideal for applications involving severe temperature fluctuations, such as in aerospace, automotive, or industrial robotics. Finally, let's consider their electrical insulation and dielectric behavior. Advanced silicones are highly regarded as excellent electrical insulators. In their molecular structure, all the valence electrons are firmly held in covalent bonds. There are no free or delocalized electrons available to flow through the material and conduct electricity. This electron-deficient framework is responsible for their high dielectric strength, which allows them to withstand high voltages without arcing or short-circuiting. Furthermore, they possess very high volume resistivity, typically in the range of 10 to the 14 to 10 to the 16 ohm centimeters. This means there is almost no electrical conduction, which efficiently prevents leakage currents. This robust insulation is critical for preventing short circuits or interference in integrated systems, where components must be electrically isolated, such as in soft actuators with integrated sensors or power systems. This combination of mechanical flexibility and electrical insulation greatly expands the design possibilities for smaller, more flexible, and power-conserving soft robotic systems.
To put the advantages of these advanced silicones into perspective, let's compare them to conventional silicone elastomers. Advanced materials offer a much broader range of stiffness, with a Young's modulus from 0.01 up to 10 megapascals, compared to the narrow 0.1 to 1.0 range of conventional ones. Their tensile strength is significantly higher, 5 to 15 megapascals versus 1 to 5 megapascals. Their elongation at break is much greater, up to 1800% versus 700%. They offer higher thermal stability and can be engineered with tailored surface chemistries for superior biocompatibility. Crucially, advanced silicones can incorporate new functionalities like self-healing, and they are compatible with modern fabrication methods like additive manufacturing, which enables complex geometries and miniaturization that are impossible with conventional molding. Now that we understand the fundamental properties, let's explore the recent advancements in the silicone-based materials themselves. These innovations go beyond just improving existing properties. They involve designing new hybrid materials and incorporating novel functionalities. One major area is the development of novel silicone elastomers. These are a significant step forward from traditional silicone rubbers, designed to meet the demanding needs of advanced applications. A key innovation has been the addition of reinforcing fillers. Nanoparticles of silica, for instance, can substantially strengthen the silicone matrix, making it more resistant to wear and tear from cyclic deformations, essential for actuators in constant motion. Other fillers like carbon nanotubes and graphene can significantly improve tensile strength, enabling the actuators to function under higher forces. These developments allow for the design of actuators for harsh environments, like industrial robotics or prosthetics, where high actuation forces and mechanical strength are required. Another promising approach is the creation of silicone polymer hybrids. This involves selectively combining silicone with other polymers, like polyurethanes, thermoplastic elastomers, or polyolefins. This allows engineers to cherry-pick the desired characteristics of each polymer to create a new hybrid material. For example, while silicones are very flexible and biocompatible, they might lack the tensile strength or fatigue resistance needed for a demanding application. Adding polyurethane can increase mechanical strength and abrasion resistance. These hybrids can also be designed to be highly responsive to environmental stimuli, like temperature or humidity, facilitating the creation of very specialized soft actuators with customized functionalities. Perhaps one of the most exciting areas is the development of bio-inspired silicone-based materials. The goal here is to create materials that mechanically mimic natural tissues, like skin, muscle, or cartilage. These next-generation silicones are envisioned to not only have engineered mechanical attributes, but also to adapt their behavior in response to their environment, just like biological tissue. For instance, a material can be designed to have the same flexibility as human muscle. This is critical in soft robotics, where actuators must interact safely and humanely with the world. Beyond simple flexibility, bio-inspired silicones can be designed with sophisticated and varying stiffness profiles, akin to the difference between bone and muscle tissue in our bodies. In a prosthetic limb, this would yield a more natural and human-like response to pressure and deformation. These materials can also incorporate self-healing capabilities. For wearable technologies and medical devices, where longer lifespans and reduced maintenance are critical, the ability for an actuator to repair minor damage on its own is a quality of very high value. Of course, having these advanced materials is only half the battle. We also need innovative fabrication methods to shape them into functional devices. A key innovation here is four-dimensional or 4D printing. This technology builds on conventional 3D printing by introducing time as a fourth dimension. The objects created are not static. They are designed to change their shape, properties, or function autonomously over time in response to an environmental stimulus, like temperature, humidity, or light. This exploits smart materials that react elastically to these stimuli. Imagine printing a flat object that, when heated, folds itself into a complex pre-programmed shape. This additive manufacturing paradigm enables the development of soft actuators that can adjust their shape dynamically, offering unprecedented flexibility. Silicones are well suited for 4D printing due to their intrinsic flexibility, broad operating temperature range, and biocompatibility. For example, thermal-responsive silicone materials can be printed with high precision to create actuators that automatically expand or contract with temperature changes, enabling self-sustaining and energy-efficient behavior without external control systems. Another powerful set of tools are laser-based fabrication techniques, such as laser sintering or laser ablation. These methods allow for the micro and nano fabrication of silicone-based actuators with intricate geometries and microstructures that would be very challenging to produce with conventional molding. Laser fabrication makes it possible to fine-tune the shape of silicone structures with very high resolution, creating complex, multi-layer geometries. This is especially relevant for soft robotic rippers, advanced medical implants, or devices with integrated sensor channels. These techniques also allow for rapid prototyping, speeding up the design of new actuator devices, and are highly scalable for production. Finally, there's micromolding. This is a highly specialized production method for producing tiny, high-precision components, often on the order of micrometers. It's essentially a miniaturized version of conventional injection or compression molding. The process involves injecting liquid silicone elastomers into precisely crafted molds with intricate internal patterns. The most significant advantage is its ability to create actuators with precise functions for use in very small or restricted areas, which is highly valuable for microrobotics and advanced medical procedures. For instance, micro-molded actuators are essential in minimally invasive surgery. Furthermore, this technique allows for the creation of large numbers of silicone-based actuators, making it scalable for the mass commercialization of healthcare devices and sensors. These fabrication advancements don't just enable complex shapes, they also facilitate the integration of novel functionalities into the silicone actuators. Let's look at some of these new capabilities. A groundbreaking functionality is self-healing. New silicone materials have been developed with the ability to independently heal damage like cracks or punctures. This is achieved by incorporating specific chemical mechanisms into the polymer network that allow molecular bonds to break and then reform upon damage.
There are two main approaches. The first is extrinsic self-healing, where a healing agent is encapsulated within the material, perhaps in microcapsules. When damage occurs, the capsules rupture, release the agent, and it reacts to repair the crack. The second, more advanced approach is intrinsic self-healing. Here, the polymer itself has an inherent ability to heal because its molecular structure contains dynamic or reversible bonds. When the material is damaged, these bonds break, but with a weak stimulus like heat or light, or even just proximity, they can reform and reattach the substance. This capability dramatically enhances the lifespan and durability of soft actuators, especially in high wear or extreme environments. Another advanced functionality is thermoresponsiveness. Thermosensitive silicones are smart materials that change their physical characteristics, like shape or rigidity, in response to temperature variations.
This is achieved by incorporating specific functional groups into the silicone that undergo a phase transition at a particular critical temperature. This causes a macroscopic change in the material's properties. In soft robotics, these silicones can be engineered into actuators that dynamically change their shape with temperature, enabling autonomous movement without external controls. For example, an actuator could be designed to expand or contract based on the ambient temperature, making it efficient and self-sustaining. Finally, there are the electroactive properties of advanced silicones. These materials can alter their shape, size, or other mechanical properties when exposed to an electric field. They are a type of electroactive polymer and have great potential as artificial muscles. The primary way this is achieved is by using the silicone as a dielectric elastomer actuator, or DEA. A DEA consists of a soft, insulating silicone elastomer film sandwiched between two compliant electrodes.
When a voltage is applied across the electrodes, the electrostatic attraction between the opposite charges, a phenomenon known as Maxwell stress, compresses the silicone film in thickness. Because silicone is nearly incompressible, this compression in thickness results in a corresponding expansion in the planar area of the material. This mechanism enables highly reversible, low-voltage controllable transformations in shape and size, making these materials a universal source of actuation in soft robotics. With all these enhanced properties, functionalities, and fabrication methods, advanced silicone materials are being deployed in a wide range of real-world applications. One of the most prominent emerging applications is in soft exosuits. These are wearable robotic systems, essentially garment-like devices that are constructed from flexible, lightweight materials, with silicone being a fundamental component. Unlike rigid exoskeletons, soft exosuits are designed to work in parallel with the human body's own musculoskeletal system.
Silicone-based actuators, in the form of inflatable pneumatic bladders or advanced DEAs, are integrated into the stretchable fabric of the suit. When actuated, these silicone components expand or contract, generating assistive forces and torques that are transmitted to the joints and limbs of the wearer. A sophisticated control system allows the exosuit to provide precise, natural support, enhancing mobility and reducing metabolic energy consumption. Their softness, lightweight, and biocompatibility make them comfortable and safe for long-term contact with the skin. These suits have meaningful applications in physical rehabilitation, in industrial settings to reduce worker fatigue, and as mobility assistance for aging populations. Another critical area is implantable devices. Silicone's high biocompatibility, environmental sensitivity, and mechanical flexibility make it ideal for next-generation drug delivery systems, biosensors, and microsurgical robots. For example, implantable drug delivery systems can use silicone actuators to accurately release drugs in response to specific biological signals, like a change in pH or temperature, enabling more targeted and site-specific therapies. Silicone-based actuators have also been used in biomedical sensors to detect specific biomolecules or environmental conditions inside the body, allowing for real-time monitoring and diagnostics. And in microrobotic surgery, which demands precision and gentle intervention, actuators made from silicone can offer flexible, minimally invasive procedures, leading to reduced recovery times and improved patient outcomes. Finally, we have soft robotic grippers. Using silicone-based actuators for grippers is a future-facing solution for manipulation tasks, especially when dealing with fragile, oddly shaped, or soft objects.
Unlike rigid grippers, these can conform to the precise shape and surface of an object, allowing it to be grasped firmly but gently. This compliance and flexibility makes them applicable in a wide range of settings, from handling sensitive biological samples in a lab to packaging food items, and even in surgical robotics for the precise manipulation of tissues and organs. So, where does this field go from here? Even with these major breakthroughs, many potential research paths are still open. A main focus for the future will be the creation of multifunctional silicones, materials that not only self-heal, but also have improved mechanical strength and biocompatibility, leading to more reliable and longer-lasting soft robots and implantable devices. Another challenging horizon is the combination of machine learning and real-time sensing within these actuation systems to enable adaptive, autonomous behavior in complex surroundings. The concept of biohybrid systems, where living cells or tissues are merged with synthetic materials to produce actuators with extraordinary functionality, is a viable future option.
On the manufacturing side, large-scale, highly precise fabrication methods will determine how far the complexity and miniaturization of soft actuators can go. And as the field moves towards wider deployment, the issue of environmental sustainability, creating recyclable or biodegradable silicones, will become increasingly important. In conclusion, advanced silicones are truly transforming the domain of soft actuators. Their unique set of qualities, high elasticity, biocompatibility, and excellent durability, combined with a growing range of sophisticated fabrication techniques, places them at the forefront of breakthroughs in robotics, medicine, and aviation. The continued development of newer materials like silicone polymer composites and bio-inspired silicones, along with advanced fabrication techniques like 4D printing, will only further augment the functionality of these devices. Continued research in this fast-growing area is bound to power revolutionary advancements in the performance and multifunctionality of silicone-based soft actuators in the years to come.